Okay, so let's write down our solution. So we'll start with circling the leading ones, identifying where they are, which columns they occupy. You can see that column 1 and column 3 contain leading ones. So that means x2 and x4 are going to have parameters. So we'll start by assigning them parameters. So I'll say let x2 be s and x4 be t, and that'll be for arbitrary s and t. In the reals, I'll put a line here to separate this work so it doesn't get mixed in. So those are our parameters. Now what's going to happen with the other two variables? Let's start that on the next page. So x3 didn't get a parameter, but its column contains a leading one. So let's write out the equation corresponding to the second row. So we've got x3 minus 3/4 x4 is equal to 0. And then we'll solve this for x3. So x3 is equal to 3/4 x4. And now if I plug in my parameter, I'll get 3/4 times t. So that's going to be x3. And then what about x? That takes care of now x4 and x2 had parameters. x3 is taken care of here, but now we have x1, whose column, the column for x1 has a leading 1. So let's write out that equation. So we get x1 minus x2 plus 1/2 x4. That's the equation corresponding to the first row. Let's solve it for the variable x1. And we're going to get x1 is equal to x2 minus 1/2 x4. And then we'll plug everything in, right? x2 is s, and x4 is t. Okay, so almost ran off the screen there. So those are our variables. Let's write the solution in column form. So we'll stack these variables on top of each other, x1, x2, x3, x4. Those are our variables. Let's write them all down, all the values. So x1 is s minus 1/2 t. X2 was what? I already forgot. X2 was s. Got that over here. Our parameters, x2 was s. x3 we had as 3/4 t. So I'll put that here. 3/4 t for x3, and then x4 was t. Right, so x4 is t, and we've got all of our variables. And then as a reminder, for arbitrary s and t. So that is our general solution now. And we will make a couple comments about that now. Remember back up when we went to the original equation, when we first wrote this down, one of the observations we made is that the trivial solution, it would definitely work. So how does this trivial solution play into our general solution that we just wrote down? Well, you can easily obtain the trivial solution. Remember, this is the solution for any s and t in the reals. That includes the values s equals 0 and t equals 0. If I took s and t equal to 0, that would make all of these coordinates equal to 0. And that's how I would recover the trivial solution. But I also get many other solutions, and that's the importance of these parameters when we write down the general solution. And notice also that we got two parameters. And you may have been tempted at the beginning, it's a common temptation in this course, to think of this as something that's going to involve one parameter, because there's 4 variables and 3 equations. And the temptation is to think that, well, maybe you're going to have a parameter for every equation that you lack, in the sense of for every variable more, or for every however many more variables you have than equations, the temptation is to think that that's going to be how many parameters you have. But this example shows that it's not quite that simple. So the full story for that was what we're going to talk about in a minute. I do want to write down a couple more definitions for that come up here about the variables before we do that, though. So we have a name for variables like x2 and x4. So let me write that down. And what I mean by that is they got assigned parameters here, right? So variables like that, if you assign parameters to variables, they're called free variables. So let's write that down. x2 and x4 are free variables. So just in other words, we're giving them parameters. And the other variables, x1 and x3, those are called leading variables. So jot that down, x1 and x3 are called leading variables. And what is it that makes a variable a leading variable? Here's how we can articulate it. When you write down the first augmented matrix, and then we do all, like, remember that came from this linear system. We wrote down the augmented matrix, we did all our row operations to carry it all the way down here to reduced row echelon form. Whichever columns contain leading ones in the reduced row echelon form matrix, the corresponding variables, so that's why I'm saying x1 and x3, because they had leading ones in their columns, those are called leading variables. So let's word it this way. This is actually difficult to write down perfectly without having it get very lengthy, so I'm going to try my best to make this brief and say their corresponding columns in the reduced row echelon form augmented matrix. Let's say that. Contain leading ones. And the way this is worded is important. So that's why I'm actually saying their corresponding columns in the reduced row echelon form augmented matrix. I have to be clear what matrix I'm talking about. So I'm not talking about, say, this augmented matrix, right? In fact, there's no leading ones in this augmented matrix. So we can't be talking about just any old augmented matrix. We have to look at the reduced row echelon form of the augmented matrix corresponding to the original linear system that we had. And of course, all those words, I don't want to write all those down. So I'm just abbreviating that by saying the reduced row echelon form augmented matrix. But really what I'm talking about is this one, the one you get when you're done all your row operations. So notice that we had a row of zeros here. And I want to come back to that in a moment. So how many parameters did we actually have in this problem? We had 2 parameters. Right? We had 2 parameters. So that's why if you go back up to the original system, you can't tell without doing some work how many parameters exactly you're going to need. But you can make some claim, and that's what I want to talk about next. But let's first make the observation in the context of this example. What it really comes down to is how many non-zero rows you have at the end of this process. Because once you turn your augmented matrix into reduced row echelon form, you may introduce some rows of zeros. And once you've done that, whatever rows are not just rows of zeros. So in this case, we've got 2 non-zero rows. In this case, that's how you can tell how many parameters you're going to need. It's not the number of variables minus the number of equations. That's a little bit too simple. It's an oversimplification of it. What you really want to do is it's going to be the number of variables minus the number of non-zero rows in this reduced row echelon form augmented matrix. That's really what it comes down to. And that's known as the free variable theorem, which we'll talk about in just a moment.